This is an example of a power factor correction. So we're going to look at a motor, a typical motor. So this is a 3-phase motor, and it has, its nameplate. It's a 50 kilowatt motor. And that 50 kilowatt motor, though, it does have a load factor of 0.8. And the motor, when you purchase this motor, it is, the rated efficiency of the motor is 90%. So I would say N is equal to 0.9. N is equal to 0.9. That's our rated efficiency of this motor that we knew about when we bought it. And the load factor that it's actually running at is running at a power factor equals 0.8. Which is not an incredible power factor. So the first question is asking, first question is asking, what is the real power? What is this real? What is the electrical power input, or the real power input? So the kilowatts in, or the real power input would be the power rating. Operating at a power efficiency, but at a power factor, but the power rating has to be divided by efficiency, because we know we would never get that amount of power. So we're going to need this amount of power to run it, the 50 divided by that efficiency. And we're going to have to also apply a power factor of 0.8 to that. So that's our 50 kilowatts of rated power times our power factor of 0.8. Power factors are unitless, divided by our efficiency of 0.9, also unitless. So this is actually 44.44 kilowatts of real power. And if we start building one of these power triangles, then that means that's this part of the power triangle, right? Real power. If we're looking at a power triangle where we're going to look at the real power, apparent power, and reactive power, and our topic here is power factor, our real power in kilowatts is 44.44 down here at the bottom of our triangle. Now, if we change the power factor, what is this going to look like? So let's look at what power factor means then. Now we're going to use the same motor. Okay, so this same motor had, since it's the same motor, we remember that power input is equal to 44.44 kilowatts, right? We can call that our real power, right? That's our real power in our power triangle. And we're going to say that the power factor is going to equal, if we change that power factor to 0.7, if it's only 0.7, let's apply a voltage to it just for this question. What's the kilovolt amps? Kilovolt amps would be our apparent power. Kilovolt amps is the apparent power. I'm just going to do apparent power in red, because it's really not that great, is it? That I have to actually provide this apparent power. And in our power triangle, then we had our real power down here in kilowatts, and that was 44.44 kilowatts. And our apparent power is the one that we know we have a power factor in there that we have to do a correction for. And our apparent power would be here. Ideally, if the power factor were 1, then this would be a straight line on top of real power, and we wouldn't have to make any reactive power to get up to that apparent power. And this is in kVA. Now we would expect this to be higher, a bigger number, right? Because we understand our power factor triangle, or our relationship between apparent power, reactive power, and real power. So we're going to expect an answer larger than the 44.4. And in reality, power factor, which in this case is in this question is changed to 0.7, is equal to the ratio of real power over apparent power. Because this is just this is a right angle triangle. So, and that is, so I can rearrange that equation. I can rearrange that equation if, in this case, I'm solving for kVA, which is apparent power. So that apparent power is going to be, if I just rearrange this equation, then it would be our real power divided by the 0.7 power factor, which would just give me then, of course, that 44.4. Oops. And you can try that on your own. 44.4 kilowatts over 0.7. Apparent power then is going to be 63.49 kilovolt amps, which is what you're going to require, and you're going to get punished for that probably by the utility in what is called a demand charge, because you didn't do any power factor correction there. What is B asking for? The current draw. What is the current draw? Well, the current draw, we're going to need to know our voltage here. Current draw, if we remember the equation, kilovolt amps is equal to √3 times the current times the kilovolts. If we remember that equation from electric motors, then it's our apparent power. We know our apparent power. Our apparent power is 63.49 kilovolt amps equals √3 times the current, times, in this question, we are given the amount of kilovolts, times 0.380 kilovolts. And so that current ends up being 96.47 amps. So you're going to have to draw a current of 96.47 amps in order for this to operate this motor, if it's at a power factor of 0.7, operating at 380 volts. So you see that there is a problem here, and if I correct this power factor, then we can reduce the amount of reactive power required, and hopefully reduce some of the demand charges charged out by our utility. First, let's finish this triangle here, though. This apparent power would then be 63.49 kilovolt amps, leaving us some reactive power that we had to had to create to offset. So we would have had to create this in order to offset that that inductive demand. So the kilovolt, and this is called kilovolt amps, reactive power here. All right, kilovolt amps reactive. And we have not calculated that. However, it would be a simple matter to calculate how much that is, because we do know this side of the triangle, this side of the triangle, and we do know that that's a right angle triangle. So now someone's saying, wow, we better correct this power factor. Let's correct it to 0.9. A lot of utilities maybe going forward are going to have a power factor even closer to unity, maybe 0.95. But right now, usually demand charges are set for anybody with a power factor of less than 0.9. So we have to see how much reactive capacitance has to be made in order to deliver that apparent power that is required in that triangle. So as we are doing this right now, what size capacitor is needed? And that basically means, what is the reactive power? What is the that part of that triangle that's going to get us up to that apparent power that we need because of the lack of power factor correction. So let's see. Again, we would just use trigonometry. We would use some trigonometry, and we would say that that reactive power is going to be equal to the trigonomic relationship of this side and hang on a second. Right, that it's going to be a trigonomic relationship. What size capacitor is needed for this one? Well, this actually is not going to ask for this whole reactive power here. This is going to ask for, this is asking for the difference between these. Let's see. If we're looking at the difference between a 0.7, this is at 0.7 power factor, and a 0.9 power factor, then we can redraw our triangle. Whoops, we can redraw our triangle here. We can redraw our triangle here and just make it a little bit more clear that we are looking at our 44.44. We're looking at our 63.49, and we went from a 0.7 to a 0.4 power factor. So we're going to actually have to look at the difference between this triangle, this total outside triangle in green, and this inside triangle in pink. So in order to do that, and I'll leave the trigonometry up to you to sort of pause and figure out, but in order to do that, we would take our one side of our triangle, and the inverse tan of inverse cos, the tan of the inverse cos of the 0.7 minus the 0.9, or however you want to work it out with your with your geometry. It's just two right angle triangles. You can take some extra steps and figure that out on your own with the two triangles. You would end up with 23.82 kVAR. And again, that's not this whole reactive power here. That is actually the difference between these two here. So this is 23.82 kilovolts amps reactant, and that is a reactive power. All right, that's my reactive power, that 23.82. And in B, what is the effect on the current? Well, we're going to have to figure out the new apparent power, right? What is the effect on the current? We would have to figure out what is that new apparent power. So that's this in the pink triangle. So this is new. This is, remember, apparent power in kilovolt amps. And remember, this down here is my real power in kilowatts. So for B, in order to figure out the effect on the current, I'm going to use this equation, kilovolt amps, basically apparent power. Apparent power is going to be equal to your kilovolts times current times root 3. Just did it in a different order than above. But what is that apparent power? But that new apparent power, so my new kilovolt amps is going to be equal to it has the 44.4 over 0.9, 49.38 kilovolt amps new. So this is 49.38. I'll just highlight it in here. This 49.38 is the new apparent power. So now we're looking at this little triangle down here, and we're saying, what is the effect on the current? And then the effect on the current, let's choose a new color here, would be if I want to solve for current here and I sub in apparent power. Remember from before that this is acting at a voltage of 380 volts it's running at. So this is where I get the 0.380 times root 3 down here, which is 75.03 amps. So we have effectively, let's just summarize what has happened here, is that what we have done is we had a 0.7 power factor up here, 0.7, and then we changed to a 0.9 power factor down here because of when we had the 0.7 power factor, the apparent power was 63.49, and down when we reduced that to when we reduced it to 0.7 as a power factor, the difference in reactive power is 23.82, bringing us to here to this small triangle where we could calculate this apparent power. And what the end effect is a current draw of 96 amps down to a current draw of 75 amps because of the efforts in correcting that power factor.